here's the reverse function on lists. So what does it do? It takes a list and gives us back the same elements in the reverse order. Let's look at this unit test down here as an example of that. The reverse of 1, 2, 3 is 3, 2, 1. The reverse of the empty list is just the empty list. How are we going to implement that? Well, here's one implementation that's possible, not the most efficient one, certainly. We'll match the list. If it's empty, just return empty. If we've got a head element followed by a tail, then obviously I want that head element to end up at the very end of the output list. So here, I will go ahead and recursively reverse the tail, right? So that here that would correspond to taking 2, 3 and reversing it to get 3, 2. And then I'll append the list containing just the single element h onto the end of it. Now, why do I say that's not so efficient? Well, this actually means that we have to walk down that whole list and create a new copy of it and append something at the end. Let's not worry about that. We're not trying to worry about efficient implementations right now. We're trying to do some interesting proofs. So that's our reverse function. Now we could try to prove that if I take a list and reverse it, and then take the length of that, well, that should be the same as just the length of the original list. Because reverse is not changing the number of elements in the list, it's just changing their order in it. So here's a theorem that states that, and we could try to prove it by induction. So we'll start off by intros the list and doing induction on the list to get our two subgoals. In the first case, the subgoal, that one's easy. Reverse of the empty list is empty, length of that's going to be 0, length of the empty list is going to be 0, so reflexivity works there. In this case, well, we're trying to take the length of the reverse of that list and the length of that list. If we simplify, both of those expressions are going to get a little bit simpler, right? So we've simplified on the right-hand side there, taken off that head element, added 1 on because it counts as 1 towards the length of the list. And here on the right-hand side, we've replaced that rev of h cons t with rev of t append h, which is exactly what the definition of rev said it should do up here. Okay. And now, if we look at the inductive hypothesis, we do have length t showing up somewhere in the goal here, in that conclusion. So we could try to use the inductive hypothesis and rewrite from the right to the left. And now we've got that the length of that expression is equal to the successor of the length of the rev of t. Now, intuitively, that makes sense to me, right? Because I've got the length of rev t here, and I know that that append of h is going to add on 1 more, and I've got the 1 more here. But to Cock, these are not equal terms. Like, I would have to reason very carefully about what's going on. In fact, if that's not clear, what if I set printing all again here so we could read it like that? Now what I've got is not so much an intuitive piece of code about lists, but like just a bunch of functions applied to a bunch of constructors. Like I've got the length function and the app function and the rev function. When you look at it like that, it's maybe a little clearer why Cock can't finish this with reflexivity or anything else at all. In fact, reasoning about what's going on with those terms requires some insight. Okay, so one thing that would help is if we could take this expression on the left-hand side apart, right? Because if we could say, well, if we took the length of rev of t, and then separately took the length of the list containing just h, well, then we'd have the length of the rev of t, and we would have 1, because that would be the length of that list. Maybe then we could make some more progress. So let's introduce a kind of lemma, a helper to prove the main theorem here, which is that length actually distributes over the append operator. Right, so if I take the length of the append of two lists, it's the same thing as adding together the length of those two lists independently. Okay, so we'll prove this by induction. And I've got set printing all on still. Let's get that off. So now I'm going to try to take the length of list 1 append list 2 and compare it to the length of list 1 plus the length of list 2. Once more, if I want to do induction on lists, it makes sense to induct on the list that occurs in the position where the pattern matches in the underlying functions are going to be most useful. And since append pattern matches on its left list argument, I'm going to induct on that list LST1. Okay. In the first goal, where that's empty, these are all going to simplify for the reasons that we've been talking about already in this video. So reflexivity suffices there. In the second goal, where I've got a list constructed with cons, actually, that cons there is going to be matched against by the append operator there. That cons is going to be matched against by length there. So simple is going to simplify both of those occurrences. And now what do I get after that? Well, I've got the successor of the length of T1 append list 2. And already I note right up there in the inductive hypothesis, I've got the same term there as I do there. So let's see if rewriting with that is helpful. Indeed it is, right? I replaced it with that separate addition of the lengths there. And now I've got, in fact, the same term on both sides of the equality. So reflexivity finishes off that proof. Okay, now with that as a helper lemma, I can complete the original proof. So here is where we got stuck roughly before. Actually, we had tried to apply the inductive hypothesis before, but that was a bad step. Let's use this app length theorem to rewrite the term on the left-hand side here to separate at that append and put a length on both sides of it. All right, now we're taking the length of the rev of t and the length of the list h. Okay, those things are going to simplify a little more now because I can replace the length of h with just 1 there. Now when I use the inductive hypothesis to rewrite, I get the length of t on the left-hand side here. And I've got two terms that are very close to one another. But of course, one adds 1 on the left-hand side. The other is using successor. Sorry, that was the right-hand side. The other uses successor on the left-hand side. So how can I resolve that incompatibility there? Well, we proved before a theorem that says add is commutative, right? So I can swap around the two sides of a plus. So if I rewrite with add commutative, it rewrites that left-hand side there to put the 1 plus on the outside. And now, of course, 1 plus itself, if I were to simplify that, would in fact put a successor constructor on the outside of length of t, and now reflexivity suffices to prove that. Of course, I didn't actually need to do the simple. Reflexivity will do it itself. Okay, so that finishes proving an interesting theorem about lists, that if you reverse a list, its length remains the same. And it also illustrates how sometimes when you get into the middle of an inductive proof, you may get stuck and you have to step back and think about, is there a lemma that I could prove that would help me make progress? This is part of getting used to doing proofs by induction in any system, whether it's on paper and pencil or an automated proof environment, a proof assistant like Coq. And here it led us to discover another interesting theorem, which is that length distributes over append.